So let's build a little table of x and y values. And in particular, I'm going to set up this table so that I know that the cube root of certain numbers is going to be perfect. For example, the cube root of 0 is equal to 0. 0 times 0 times 0 gives me 0. Now if x is 8, then 2 times 2 times 2, or sorry, we'll even use 1. 1 times 1 times 1 is 1, so the cube root of 1 is 1. Similarly, for negative 1 times negative 1 is positive 1, times negative 1 is negative 1. So here's so far what this graph would look like. When x is negative 1, the output would be negative 1. When x is 0, the output would be 0. When x is positive 1, the output would be positive 1. Similarly over here, if I pick negative 8, negative 2 times negative 2 times negative 2 we just found out was negative 8. And similarly for positive 8, the number would be positive 2. So 2, 3, 4, 5, 6, 7, 8, we would get an increase in x of 1. So notice that takes a real good amount of time or a good amount of input values to be able to increase the output by 1. Now similarly, for x is negative 8, the output is positive 2. So it looks kind of like this elongated S shape. And just to verify that, let's just go ahead and create a graph. We will just do, well, the cube root, we actually have to come over here to our math functions and pick option 4. So the cube root of x would kind of look like this. So you can kind of see that at x equal, whenever the radical is 0, the output is also 0. So what would you imagine would happen if I made the radical, or the thing under the radical, negative 3, x minus 3? Well, from our previous experience, at x equals 3, the output will be 0. And when that happened, the graph shifted right 3 units. So notice that we get the same graph, except if it's x minus 3, it requires an x value of positive 3 to make it 0. And so we get the same elongated S shape, but it's sort of shifted over this direction. Let's consider a real application of this idea. Let's take a look at an example. So the time, this is actually a real world example that can be used to determine drop times. The time in seconds it takes a diver to reach the surface of water in a pool from a diving board that is h feet off the ground is given by the function t equals the square root of 1/16 times the height of the diving board. So this is kind of hard to read right here, but it says, what can be said about the amount of time it takes to reach the water's surface as the height of the diving board gets higher? Well, you can probably imagine what's going to happen. If this is you up here on the diving board, then the higher that diving board gets, the longer it's going to take. So if that rises a little bit more, it's going to take you a little bit longer to reach it. However, if we plot this function and we take 1/16, or the square root, we'll do the square root, and then I'll do parenthesis 1/16 times x, and whoops, and I just take a look at the graph of this. Let me kind of zoom in just a little bit, so set my window a little bit lower, and maybe I don't really need to consider negative heights, and I don't need to consider negative times, so let's just do maybe 0 to 100. Well, as we can see, the amount of time it's going to take so this is the height of the diving board. As the height of the diving board increases, the time it takes also increases, but notice that it doesn't take that much longer. For every additional foot, the pool increases in height. So the question is, or one question we might have is, how long will it take a person diving from 100 feet to break the surface of the pool? Well, this would involve us figuring out, I'm going to go over to second graph to look at the table. I'm going to set my table at 0 and have it increase by 100 so that I can see this in 100-foot increments. And I notice that when I go to my table, it says that for a 100-foot dive, it's going to take 2.5 seconds. We could similarly find this by plugging in 100 in for h.